Hi everyone, I'm Adrian from the Australian Computing Museum, or the ACMS, based here in Sydney, New South Wales, Australia. At the ACMS, we have one of the largest digital equipment corporation collections anywhere in the world. We were founded in 1994 by many people, including Max Burnett, one of the first employees of Digital Australia. DEC was founded in 1957 in Maynard, Massachusetts, and grew to be one of the largest computing companies in the world. In our collection, we have a significant amount of documents, computers, and training material. And today, we're going to present some of that training material to you in the form of old VHS tapes. So please sit back, relax, and enjoy. Thank you.
The VAX family of general-purpose computers offers the broadest range of compatible systems in the computer industry. VAX systems are being used throughout corporations, on desktops, in departments, in data centers, and on the shop floor. VAX systems encompass the full range of computing power, from workstations used by a single person to high-performance systems supporting hundreds of users. Despite these differences in size and performance, users of all VAX computer systems can communicate with each other, work on common programs, and share data and system resources. How is this communication and sharing possible? All computers in the VAX family are compatible. Compatibility allows users to run the same software and to execute the same programs on any VAX computer, small or large, with little or no modification. This unit shows how this compatibility is achieved. We'll examine the two main elements of the VAX computer family. One element is Virtual Address Extension, or VAX, a common 32-bit computer architecture. The second element is the Virtual Memory System, or VMS, the standard operating system used by all computers in the VAX family. This unit introduces the general features of the VAX architecture and the VMS operating system. Many of the basic terms and concepts used throughout this course will be discussed. The unit consists of two lessons. Lesson 1 focuses on the VAX architecture, the architecture shared by all members of the VAX computer family. Lesson 2 introduces the VMS operating system, the standard operating system run by all VAX computers.
We'll begin Lesson 1 by examining the term architecture. What do we mean by architecture? An architecture consists of the fundamental attributes that make something what it is. Another way to think of an architecture is as a specification of how something functions. Consider the following analogy. A piano is an instrument that produces music by means of a keyboard and a system of wires and hammers. The keyboard is central to the piano's architecture. It contains a standard number of white and black keys. Pressing a key causes a note of a specified frequency to be produced. An architecture is intangible. In the case of the piano, the keyboard itself is not the architecture. Rather, it's actually the relationship of keys to notes that makes up the architecture. That is, the number of keys and the specific note generated by each key define the piano architecture or its specification. Many different pianos can be built around the single piano architecture. Keys may be made of ivory, wood, or plastic. Cabinets come in a variety of sizes, shapes, and materials. We refer to these various models as implementations of the same piano architecture. A musician who can play one piano can play any piano because of a single architecture common to all pianos. Similarly, a piece of music written for one piano can be played on any other piano. The distinction between architecture and implementation is important. An architecture is independent of its outward physical form. An implementation is the specific physical manifestation of an architecture. Just as the piano's architecture is the means by which musicians create musical compositions, the architecture of a computer system, such as VAX, is a specification describing the basic functionality available to system programmers. Said another way, a computer architecture defines things, such as the instructions available to perform computer operations, the types of data the computer can work with, the methods of locating data, and so on. A computer implementation, on the other hand, is the physical organization of that architecture from specific hardware components. Many different VAX models exist, all of which share the same VAX architecture. What are some of the hardware differences among VAX computers? CPU speed and performance can vary from one VAX model to another, as can the memory capacity and speed, and the way the input-output subsystem is implemented. Thus, while many implementations of VAX computers are possible, each of them embodies the same architecture that makes it a VAX. Let's turn now to the general characteristics of the VAX hardware architecture. Every VAX central processing unit contains 16 general registers, which can be used in a number of ways. For example, the registers can serve as temporary storage locations for data that the CPU is operating on, or they can contain addresses of data stored in memory. To define how these registers are used, the VAX architecture provides over 20 different addressing modes. The addressing modes allow programmers to specify how the CPU is to access data to be operated on. For example, one addressing mode indicates that a register contains the data for an operation. Another addressing mode indicates that a register contains an address pointing to data located elsewhere. A number of other modes are defined as part of the VAX architecture. We'll describe these addressing modes in a later unit. The addressing modes work together with the VAX instruction set. Over 300 instructions are included in the VAX architecture. The instructions determine the fundamental operations to be performed by the CPU's arithmetic logic unit, or ALU. For example, there are instructions such as add, which are used for arithmetic operations, and instructions such as compare, used for logical operations. Many instructions are also used in conjunction with data types. The way in which the ALU interprets data is defined by the data type employed. For example, if integer data is specified for use with an add instruction, the data is interpreted one way by the ALU. But if the same add instruction is used with floating point data, the ALU will interpret the data differently. The availability of different ways to represent data provides programming versatility and allows very compact programs to be written. Another attribute of the VAX architecture is the 32-bit virtual address used to reference program data. Virtual addresses are generated by programs executing in the CPU. The name VAX, or Virtual Address Extension, reflects the significance of virtual addresses to the nature of the architecture. A virtual address is so called because it is not the actual address of a physical location in memory. Rather, it is a reference to data that must be located for the executing program. In order to find the actual locations of data, the CPU must translate all virtual addresses into physical addresses. The physical address can then be used to access the data stored in physical memory. With 32 bits available for addressing, the VAX architecture provides a very large virtual address space of 2 to the 32nd power, or over 4 billion bytes, more than enough for current and future programming needs. The term address space refers to the total number of possible addresses. In conclusion, the VAX architecture includes a number of elements of interest to programmers and system managers. In this course, we'll focus on several significant ones. 16 general registers may store either data or addresses of data found in memory. Over 20 addressing modes determine how the general registers are used to access the data to be operated upon. More than 300 instructions define the operations to be performed by the CPU's arithmetic logic unit. These instructions operate on a wide variety of data types to make programming flexible and powerful. Finally, a 32-bit virtual address allows for an address space of over 4 billion bytes. All VAX computers, regardless of model, share these attributes. This concludes Lesson 1, an overview of the VAX architecture. Before continuing on to Lesson 2, please turn to your course reference guide and review the information for Lesson 1. In this lesson, we'll introduce VMS, the operating system that runs on all VAX computers. VMS manages the entire hardware and software environment. It consists of a group of internal programs and utilities that allow the system and its users to communicate with each other. VMS stands for Virtual Memory System. Virtual memory is the means by which VMS achieves its large addressing capacity of 4.3 billion bytes. Virtual memory works by combining physical memory with disk storage in such a way that the computer appears to have more memory than it physically contains. This makes it possible to accommodate programs and data which exceed the capacity of physical memory. In this virtual memory system, data is passed back and forth between disk storage and physical memory as needed, in much the same way as you might use a note card filing system. You pull out a card, find the information you need, then refile it until you need it again. Because of the ability to pass data in and out of memory as needed, not all of a program needs to be in physical memory at one time. This capability allows programmers to write very large programs without being constrained by the size limitations of physical memory. The active portion of the program can reside in memory, while the other parts are held in auxiliary storage until they're needed. The VMS operating system is a multi-programming environment. This means that multiple programs can reside in memory concurrently. VMS keeps track of where all the parts of each program are at any given time, and makes room in memory for the most active parts. Let's contrast this with a single program system. In a single program system, only one program at a time can reside in memory. The program can be either running in the CPU or waiting for some event to happen, for example, completion of an I/O operation. A program that spends the majority of its time doing computation is called a compute-bound program. Thus, a program that computes pi to 1,000,000 decimal places is compute-bound because it spends a lot of time computing each digit and only rarely writes data to a peripheral device. A program is called I/O-bound if it has many I/O requirements in proportion to its computation requirements. An example of an I/O-bound program is an airline reservation system, which spends most of its time waiting for a request from a clerk or for information to be transferred to or from disk storage. With I/O-bound programs, the CPU is idle much of the time. Thus, CPU use can be very inefficient in single-program systems. By contrast, in a multi-program environment, many programs share the same CPU. For example, when Program A pauses to wait for an I/O operation, Program B takes over the CPU. Multi-program environments ensure the efficient use of CPU time. When a program must wait for the completion of an I/O operation, another program can use the CPU. In a multi-programming environment, programs can be in one of three states: run, wait, or ready. In the run state, the program has control of the processor. Only one program at a time can run unless more than one processor is available to the system. A program in the wait state cannot execute at the moment because it's waiting for an event, such as an I/O completion. While only one run state exists, many kinds of wait states are possible. Wait states are classified by the type of event anticipated. So it's possible for programs to be in various wait states because they're waiting for different events. The third state is the ready state. A program is considered ready when it could be executing but isn't because another program is in the run state. Transitions, shown here as arrows, occur when events cause a program to change from one state to another, such as the transition that occurs when an I/O request has been completed. In this situation, a program that was waiting enters the ready state. It can now be scheduled to run when the CPU becomes available. Until now, we've been referring to programs as the entities in various states in the CPU. However, it is more accurate to refer to images. In VMS, a source program must go through a conversion process in order to become machine executable. The source code, which may be written in a high-level language such as Fortran, is compiled to produce an object program. The object program is in machine language. However, the object program must be linked to find addresses of any external information. The result of this operation is a machine executable image file. An image, however, doesn't execute by itself. It executes in the context of a supportive environment called a process. We'll use this symbol to represent a process. In a later unit, we'll explain the different parts of the process represented by the symbol. The process is the basic scheduling unit in VMS. Because processes are scheduled, it is more appropriate to refer to process states rather than program states. A process is said to be in the current state if it has control of the CPU. In a single processor system, only one process at a time can be current. A process in the wait state is inactive until some event is completed or a condition is satisfied. Many kinds of wait states are possible, each related to the event or condition the process is waiting for. For example, a process can wait while VMS goes out to disk to find data. Once the condition is satisfied, the process becomes computable. The process is ready to execute but does not yet have control of the CPU. We'll describe the events which cause a process to move from one state to another in a later unit. We've seen that VMS is an operating system which uses virtual memory. Virtual memory combines physical memory and disk storage to provide programmers with a very large address space for programs. As a multi-programming environment, VMS performs the following functions. It schedules CPU time for processes in various states of readiness, manages the efficient use of memory, and coordinates all system resources. We'll examine these functions in much more detail later in the course.